Okay, so we're going to go ahead and continue with the titration and pH curve analysis, but in this case we're going to be looking at situations in which weak acids or weak bases are present. So we're going to just go ahead and look at the titration of a weak acid with a strong base. Okay, so basically in this situation we are titrating 50 milliliters of 0.10 molar HC2H3O2, okay, otherwise known as acetic acid. And basically we're titrating that with 0.10 molar NaOH. So in this case, in the Erlenmeyer, I have a weak acid, and in the burette, I have a strong base. Okay, so if we look at the titration curve of this weak acid strong base titration, hey, you're going to notice some big differences between it and the strong example that we looked at. Okay, so if we go ahead and take a look at this curve, okay, first of all we notice we start at a slightly higher pH. Obviously we would anticipate something like that happening when we start with a weaker acid in solution. There's subsequently going to be less H+ naturally residing in that Erlenmeyer flask. Okay, also I want you guys to notice at the equivalence point you do not have a pH that is equal to 7, you have one that is slightly basic. Okay, so these are just some features that you would be able to quickly notice and differentiate this titration process from a strong titration curve. Okay, so make sure that you're looking at that initial starting pH and of course the pH at that equivalence point to help you differentiate between a strong and weak strong titration curve. Okay, so let's go ahead and let's do some calculations for our titration curve for this weak strong titration series. Okay, so before any NaOH has been added, we first need to figure out that pH value. Okay, so we consider the species present. Of course, we have we have the acetic acid present and water. Okay, now the pH is obviously going to be determined by the H+ present in solution. And basically, just like we have been treating all of the other weak acid situations, if we want to figure out our H+ concentration, we're going to need to use an ice table, the equilibrium expression, and of course that Ka value. Okay, so we set up that ice table, we figure out the changes that are going to occur, we figure out the concentration value expressions for the acids and obviously the conjugates that are produced at equilibrium. Okay, we subsequently plug them into the equilibrium expression. In this case, we're going to make the assumption that the change in x is very small. Okay, so we drop it off, check it. Obviously, if our x value is less than 5% of the original concentration, then we can use this assumption, which is acceptable in this case. That subsequently gives us our x value. We take that x value, which corresponds to H+, plug that into our pH equation, and subsequently get our pH value of 2.8. So as we start this reaction, when we've added 0 NaOH, our pH is 2.87. Okay, so let's go ahead and let's look at the rest of this. Okay, so the next point is going to occur once we've added 10 milliliters of 0.10 molar NaOH. Okay, so at this point, guys, obviously we still have our acid present, and now we've added hydroxide ion. Okay, and we know that hydroxide is going to react with acetic acid to produce the acetate ion and water. So stoichiometrically speaking, we have our acid and our added base, okay, and we have our subsequent products. Now, we need to go ahead and pay attention to the presence of this conjugate base because it has an effect on our pH value. Okay, so basically we look at the number of moles of each of our substances that we've added, just like we were doing with the strong examples. We're taking our volume times our concentration values, we get our moles. Okay, these are going to react in a 1-to-1 fashion, so the amount of H+ is going to decrease by the amount of hydroxide moles added. Okay, so obviously the subtraction here gives us this 0.004 moles. Okay, all the hydroxide ion is going to get used up because we have an excess of H+. Okay, and additionally, guys, we need to pay attention to the fact that this acetate ion is actually going to remain in solution. So initially we don't have any, but after this ionization process, okay, we end up with 0.001 moles of this acetate ion. So now that we have added that 10 milliliters of NaOH, and we subsequently figured out our species that remain in solution that actually affect the pH, we need to go ahead and obviously calculate our pH values. Okay, so how are we going to do that? Well, obviously we're going to consider this process, the ionization process associated with the acid that's in solution, because obviously its presence as well as the presence of its conjugate are going to dictate how much H plus remains in solution. Okay, so what do we need to do? We're going to set up our ice tables, okay, but for our initial values that we're going to utilize, we're going to look at the amount of acetic acid that remains after the hydroxide ion production. Okay, we're going to divide that by the total volume of our solution, so the 50 milliliters of the acid that we started with and the 10 milliliters of the sodium hydroxide that we added. That gives us our concentration of the acid after that first addition. Okay, same concept is going to be applied here to the acetate ion that's remaining in solution. Okay, we get that concentration. We subsequently set up the changes and of course figure out our equilibrium concentration expression values. Okay, we then substitute this or plug these numbers into our Ka equation. We know our Ka value. Okay, we subsequently plug in our values here. Okay, solve for X just like we've done tons of times before. X is going to correspond to H3O plus. H3O plus, or H plus in this situation, is 7.2 times 10 to the negative fifth. Okay, and if we plug that into our negative log calculation, that'll give us our pH of 4.4. Okay, so notice our pH has continued to rise as we've continued to add more base. Okay, so let's go ahead and continue with these calculations. Okay, so let's go on to move to point B. Okay, at this point we've added 25 milliliters of the sodium hydroxide. Same concepts and same approach to the other calculations that we've done. Obviously we're looking at the interaction between the acetic acid, the hydroxide ion, and obviously the conjugate-based acetate ion that's produced. Okay, we figure out the number of moles present before any addition. We figure out the number of moles of hydroxide ion that have been added, and we subsequently look at the changes. Obviously we see a decrease in the amount of acetic acid that's present, and an increase in the concentration of acetate ion that is present. Okay, so at this point I want you guys to notice a little detail that the moles of acetic acid and the moles of acetate ion are equal. Okay, and we'll talk about that a little bit later, but I just wanted to point that out. Okay, so we're going to go ahead and do our calculations. Now, obviously we've used up all of our hydroxide ion that we just added. Okay, and we're going to look at how acetic acid ionizes into the acetate ion and the H+. Okay, we take our ice table, we set that up, we figure out the concentration of acetic acid and the concentration of acetate as we did in prior examples. Okay, then we're going to obviously figure out our change in our concentration and subsequently establish our equilibrium values. Okay, we plug these equilibrium values into our Ka expression and subsequently solve for X. Okay, and in this case, notice that your X value, which is also equal to your H plus, is equal to the 1.8 times 10 to the negative 5, which is the same as your Ka. Okay, we plug this value into our pH calculation and get 4.74 as our pH value. Okay, now there's a few things we want to point out at this point, okay, in this next slide. So something else I want to point out about point B is that this is actually known as the halfway point, okay? This is a little bit more important, I guess, with weak, strong situations, but basically, as you can see from this titration curve, at 50 milliliters addition of NaOH, we're going to reach our equivalence point. Okay, so the 25 milliliters that we've just added is known as the halfway to equivalence. Okay, so at this point, the concentration of the weak acid and the concentration of the conjugate base that's produced are going to be equal. Okay, so at the halfway point of weak acid strong base titrations, your H plus concentration is going to end up equaling your Ka value, and your pH will subsequently equal your pKa. Okay, so continuing on, adding 40 mils at point C. Okay, same exact calculation approaches, same idea that we've been doing over and over. We get the number of moles of our acetate ion, the number of moles of our acetic acid, okay, and we're going to subsequently plug these in to the expression that allows us to calculate our concentrations of our acetate and our acetic acid and our acetate ions. Okay, we plug these in, get our values, plug them into the equilibrium expression, subsequently solve for x. X gives us our H+, take the negative log of it, and we subsequently get our pH of 5.35. Okay, so that's point C. Now let's continue on. Okay, point D. Okay, at this point we've added the 50 milliliters of the 0.1 molar NaOH. Okay, so stoichiometrically speaking, okay, the amount of acetic acid and the amount of hydroxide that's been added are equal. Okay, so that's going to give us 0 moles of each of them remaining. So at that point we know that we have reached our equivalence point, okay, because the H+ and OH- ion concentrations can be viewed as being equal. Okay, however, remember we talked about the fact that the pH at the equivalence point of a weak strong titration situation is going to be different than what is expected at or in a strong situation. And the reason why, guys, the reason why we have a higher pH here is because, remember, we have this conjugate of the weak acid. And remember that they behave as either acids or bases in solution. In this case, it's the conjugate base of a weak acid, so this is going to behave as a base in solution. So our pH is going to be a little bit higher than in a strong situation. Okay, so obviously the number of moles of our hydroxide and our acetate ion are equal, our hydroxide and our acetic acid are equal. Our acetate ion remaining is as follows. Okay, so we're going to go ahead and calculate our pH at this equivalence point. Okay, so if we go ahead and look at this, pH is obviously going to be determined not by the H+ or OH- present from the weak acid or the strong base that's being added, but in fact by the acetate ion that remains behind. Okay, so really what we're looking at is how this conjugate base behaves as a base in solution. So we go ahead and subsequently plug it in to this expression in the ice table. We find its concentration, we find the changes, okay? And then what we need to do is we actually need to plug this into the Kb value of this expression. So the question may be, well, where are we getting this Kb from? Where's that value coming from? Well, remember, we were given the Ka of the acetic acid, okay, 1.8 times 10 to the negative fifth, okay, and we know that Ka times Kb equals Kw, okay, so this allows us to solve for our Kb value without having to do any, super complicated calculations. Okay, so we plug this, these equilibrium values into our expression, and we subsequently solve for x. X is going to correspond to the concentration of our hydroxide ion in solution, which is obviously going to help determine the pH. So we subsequently figure out that our hydroxide ion concentration is as follows. Okay, once we figure that out, we can then use the pH plus pOH equals 14 to solve for our pH value, because remember, I first have to calculate my pOH here. And subsequently, we get an equivalence point of 8.72, which is pretty close to 9. Okay, so notice the equivalence point, guys, is much greater than 7, and that's because of the presence of this conjugate base of that weak acid that's floating around in solution. So expect this kind of difference in your equivalence point for weak strong situations. Okay, and obviously if we continue to add base, our pH is only going to increase as we see here in the curve. Okay, so we approach the stoichiometry just like we have been. Okay, remember we used up all of our acetic acid. Okay, after we've used up all of our acetic acid, there's going to, of course, be some hydroxide ion concentration remaining, and of course we're going to continue to have that constant value of the acetate ion because we've picked up all the H pluses and produced a bunch of water. Okay, so we can take these values and subsequently use them to do some additional calculations to figure out our pH. So if we go ahead and continue to look at this addition, the way we're going to figure out our concentration of hydroxide ion is basically take our moles of hydroxide, okay, divide by the total volume, just like we've been doing, okay, and subsequently get our OH minus concentration, and subsequently get our pH at 60 milliliters sodium hydroxide being added. Now, obviously, the bigger contributor to that pH change is going to be dictated by that hydroxide, that strong base that's actually in solution. So basically, the acetate ion presence is not really a huge factor in terms of determining pH value at that point. Okay, so let's look at the comparison between strong and weak titrations. Okay, so before the equivalence point occurs, obviously they're very different. So strong acid, strong base versus weak acid, strong base titration. Okay, so notice the acid strength is what's different here. Okay, so notice that the values or the pH before we've reached equivalence point are going to obviously be different, right? They're going to be a little bit lower for the strong acid versus the weak base. Obviously, the strong acid is going to have a little more H plus in solution. Okay, for the weak acid, the pH is going to increase more rapidly at the start and basically start to level off near that halfway point when the HA and A minus concentrations are equal, right? So you have that optimal buffering situation. Okay, and basically we then expect them to obviously increase very rapidly again right before the equivalence point because we've gone past any buffering capacity. Okay, for the point past the equivalence point, the change is going to be pretty drastic for both because at that point you're just adding a bunch of strong base to the solution. So that excess hydroxide ion concentration is really what's going to be dictating it. Okay, and as we discussed, the equivalence point location for a strong versus a weak strong is drastically different. We know that the pH of the strong titration is going to be 7, and that's because H2O is the determining factor. And we know that its pH is going to be associated with 7. Now, for the weak strong situation, we know that pH is going to be greater than 7, and that's because we're going to have the presence of the conjugate base. And that conjugate base of a weak acid behaves as a base in solution and subsequently produces hydroxide ions. So at the equivalence point, you still have the H plus and OH minus being equal, but the presence of this conjugate base causes an increase in that overall pH value. Okay, so things to note. Okay, so the amount of weak acid present, not its strength, determines the equivalence point. Remember, your Ka values obviously dictate, the strength of your acid. The larger the Ka, the more H plus you put into solution. Okay, but if we look at, two different acids with different Kas, as we see here in this example, okay, what ends up happening is obviously we see a Ka of 1.8 times 10 to the negative 5 and a Ka of 6.2 times 10 to the negative 10. Now, we are titrating both of these with the same amount of sodium hydroxide. Okay, so because we're titrating them with the same amount of sodium hydroxide, and because they're both reacting in a 1-to-1 ratio, the equivalence point for both of these processes are going to be exactly the same, right? The moles of hydroxide ion needing to cancel out all the H plus is the same in both examples. So it doesn't matter the Ka values. However, the acid strength for these situations, these weak, strong titrations, does affect the pH at the equivalence point. Because remember, we're using the Ka values for these specific reaction types, and your pH value is going to subsequently be related to the Ka value you plug into that equilibrium expression. Okay, so if we look at acetic acid and hydrocyanic acid, notice that their pH values are different at the various equivalence points. Okay, so other things to note, the weaker the weak acid, the greater the pH value at the equivalence point. Okay, so if we look at a couple of values of Kas, notice that the smaller the Ka value, the bigger that pH value that corresponds. And that's because the conjugate base that's produced is going to behave as a stronger base and subsequently put more hydroxide ion in solution and subsequently give you a higher pH value overall.